The Cosmic Connection, an Extraterrestrial Perspective by Carl Sagan. And right up front, I need to clearly identify Jerome Agel separately and accurately as the editor of this work. He's not a co-writer, just to be clear. He is the editor. Today, our purpose is to explore what planetary science, astrobiology, exoplanet astronomy, and SETI reveal about the possibility of life beyond Earth, which leads us to our central question for this deep dive. What does modern astronomy reveal about the possibility of life beyond Earth, and how would discovering extraterrestrial life change humanity's understanding of its place in the cosmos? So, to answer that, we're basically tearing up the old maps today. We'll start by grounding ourselves in Sagan's cosmic perspective, looking at how astronomy and exploration are really fundamentally human enterprises.
Right.
We'll review the messages from Earth we've already sent out. Then we're going to act like interplanetary detectives. We'll use comparative planetology to check out Venus and its severe planetary climate warnings.
Right.
And we'll trace the path of Mars from those early imagined canals to the Viking landers, diving into the really intense difficulty of actually detecting life.
It's harder than people think.
It really is.
Yeah.
And from there, we'll venture further out to Europa, Enceladus, Titan, and other ocean worlds. We'll expand our definition of habitability by looking at origin of life research and extremophiles.
Yeah.
Once we exhaust our solar system, we'll jump to the wider galaxy to see how exoplanets, habitable zones, red dwarf systems, and atmospheric characterization just completely transform the question.
Totally changed the game.
Right. We'll examine biosignatures and false positives, and then shift our focus from biology to technology. Hunting through radio SETI, optical SETI, and wider technosignatures. We'll look at the Drake equation, confront the great silence of the Fermi question, and finally grapple with the massive realities of interstellar travel, terraforming, planetary protection, possible contact, cross-cultural communication, civilizational development, and humanity's changing cosmic identity. Okay, let's unpack this.
I mean, it is a staggering itinerary. But to make sense of this whole detective story, we first have to understand how the magnifying glass itself has changed.
Right.
Our map of the universe has been completely redrawn since this book was first published.
Yeah.
We're actually looking at three distinct eras of evidence here.
Okay.
You have 1973, which was Sagan's original scientific context. And back then, planets were mostly just, fuzzy points of light in telescopes.
Sure.
We had absolutely zero known exoplanets.
Wow.
Zero. And spacecraft exploration was just in its absolute infancy. Then you jump to the year 2000 with the Cambridge edition. That update offered these major reassessments following decades of planetary missions that just totally shattered our early assumptions about Venus, Mars, and the outer solar system.
Because we actually sent hardware there and realized the solar system was wilder and much more hostile than we thought.
Very much so, yeah. And that really sets up the modern era. For this discussion, our research cutoff is August 19, 2026.
Yeah.
Today, we have the James Webb Space Telescope conducting these deep atmospheric studies of distant worlds. We have expansive ocean world research right here in our own system. And crucially, as of August 6, 2026, we have 6,336 confirmed exoplanets.
That is just a wild number compared to 0 in the 70s.
It's unbelievable. Because the sheer volume of data has exploded so much, modern astronomy requires a very strict ladder of confidence. We have to meticulously separate confirmed astronomical properties, like physically measuring a planet's mass or its orbital period.
The concrete stuff.
Exactly. We have to separate that from model-dependent interpretations, like simulating what its ancient climate might have been. And we must separate both of those from active research and existential conclusions about life.
So it has the difference between proving this planet has a thick atmosphere and claiming this planet has alien forests breathing in that atmosphere.
Right.
We have to keep our feet on the ground.
Which is exactly why establishing that ladder of confidence is so crucial right at the outset. I need to state explicitly, as of this 2026 cutoff, no extraterrestrial organism, except an exoplanet biosignature or confirmed technosignature, has yet been established.
I love starting with that baseline, because if we haven't confirmed life out there yet, it kind of forces us to ask, how do we even know what we're looking for? Right?
Yeah, exactly.
To figure that out, we really have to use our own solar system as a set of planetary control cases, comparative planetology. Take Venus, for example. For a long time, scientists looked at Venus, same size as Earth, similar gravity, covered in clouds, and they imagined this lush, tropical, swampy world.
It was a very human assumption. I mean, we projected our own prehistoric Earth onto it. But when spacecraft finally pierced those clouds with radar and those early descent probes, the reality was a brutal planetary climate warning.
Yeah.
Venus is characterized by scorching surface temperatures hot enough to melt lead, incredibly dense carbon dioxide atmosphere that would crush a submarine, and intense planet-wide volcanism.
So what actually happened to it? I mean, how does a planet so similar to ours turn into a literal hellscape?
It perfectly demonstrates how physical systems have thresholds.
Right.
Early Venus likely had oceans, but as the sun gradually grew brighter, those oceans began to evaporate.
Right.
Water vapor is a potent greenhouse gas which trapped more heat, which evaporated more water. This runaway greenhouse effect baked the carbon dioxide right out of the rocks and into the atmosphere, creating an environment entirely hostile to known life.
Wow.
It's a stark reminder that an Earth-sized planet can easily evolve into a completely dead world.
A climate control group gone catastrophically wrong.
Yeah.
And then swinging to the other extreme, you have Mars. The history of Mars exploration is just a masterclass in how human expectations shape observations.
Oh, absolutely.
Back in the early 20th century, astronomers looked through these blurry telescopes and thought they saw canals, imagining a dying, desperate civilization trying to irrigate its desert.
Right, the Lowell observations.
Yeah, exactly. But when orbiters and rovers actually arrived, we found undeniable geological evidence of ancient water-dry river deltas, sedimentary rock, lake deposits, but absolutely no canals.
None.
Mars went from a sci-fi fantasy to a cold, irradiated desert that simply used to be wet.
And that geological reality of a once wet Mars is really what motivated the Viking landers in the 1970s. They were dedicated to direct biological experiments.
Right, the scoopers.
Yeah, they scooped up Martian soil, injected it with a nutrient broth, and tested it for metabolism-like reactions. And initially, the soil was highly reactive. It released gases that looked exactly like respiration.
But it wasn't breathing microbes, was it?
No, it wasn't. It turned out the Martian soil was packed with perchlorates, these highly reactive chemicals created by ultraviolet radiation hitting the dirt.
Wow.
Unfamiliar geochemistry can easily imitate biology. The Viking missions were a very sobering wake-up call. They proved just how intensely difficult life detection actually is, establishing the modern requirement for multiple independent biosignatures and extreme caution before declaring a discovery.
So if the traditional habitable zone, the orbital area where a planet receives just enough sunlight for liquid water to pool on the surface, if that isn't a guarantee for life, maybe we need to look in the shadows. We have to venture further out to the ocean worlds of the outer solar system, where the energy source isn't the sun at all.
Right, and this is a revolutionary shift in planetary science. When you look at moons like Europa orbiting Jupiter or Enceladus orbiting Saturn, they're locked in a gravitational tug-of-war. The massive pull of the gas giants, combined with the pull of other neighboring moons, literally stretches and squeezes these worlds. Imagine solid rock and ice flexing by meters every few days. This internal friction generates immense heat, a process called tidal heating.
So the ice melts from the inside out.
Exactly. Underneath miles of frozen crust, Europa has a deep, dark global ocean containing more liquid water than all of Earth's oceans combined.
That is just wild to think about.
It is. And Enceladus is actively shooting massive plumes of water, salts, and organics out into space from its seafloor, where we suspect hydrothermal vents exist.
Wow.
And then you have Titan, Saturn's largest moon, which has a thick atmosphere and an active weather cycle. But it's so cold there that the lakes and rain are made of liquid methane and hydrocarbons rather than water. It's an entire natural laboratory for alternative chemistry.
Okay, let me push back on this for a second, because this is where people get really excited, right?
Sure.
If we are detecting complex organics spewing out of Enceladus, or we find more evidence of ancient water and organic compounds on Mars, doesn't that mean life is or was there? I mean, it's like finding ashes and assuming there was a campfire, right?
It's an incredibly tempting analogy, but we really have to correct that assumption carefully. Organic molecules are not proof of biology.
Okay.
They are simply carbon-based compounds. In the vast chemistry set of the universe, they can form through completely natural, non-biological reactions. Furthermore, a potentially habitable world is not necessarily inhabited. An ocean is just a setting. It doesn't guarantee that the complex spark of life ever occurred there.
So the stage being set doesn't mean the actors ever showed up. But if we want to figure out how the actors get there in the first place, we have to look back at biology here on Earth. origin of life research, and extremophiles.
Right. We used to think life required very specific, pleasant conditions. But then scientists discovered microbes and complex ecosystems thriving in extreme environments on Earth.
Like the deep ocean.
Yeah, deep-sea hydrothermal vents, where toxic chemicals spew out of the crust, or acidic hot springs, subglacial lakes deep beneath Antarctica. This proves that life doesn't strictly need sunlight or comfortable temperatures. It dramatically broadens what we consider a habitable target.
But there is a catch, isn't there?
Yes. The catch is that these extremophiles are still Earth life. They share our DNA ancestry. They don't prove that life originates easily in extreme environments, only that once life exists, evolutionary adaptation is incredibly resilient.
Ah, I see.
Astrobiology is still wrestling with the biggest mystery of all. How does non-living chemistry cross that threshold into self-replicating, evolving biology?
And while the biologists are trying to solve that puzzle, the astronomers have just blown the doors off the observatory. The thousands of confirmed exoplanets have totally transformed the statistical question. We aren't squinting at the sky guessing if other stars have planets anymore. We know almost all of them do.
The technological leap is profound. We find most of them using the transit method, watching a star dim ever so slightly when a planet crosses in front of it. We also use radial velocity, measuring the subtle gravitational wobble a star exhibits as an unseen planet tugs on it.
And a lot of these discoveries, like the famous TRAPPIST-1 system, are happening around red dwarf stars. Why is that? Are they just better hosts for life?
Not necessarily better for life, but much better for our current telescopes.
Oh, okay.
Red dwarfs are incredibly common, but they are much smaller and cooler than our sun. Because the star is small, a planet blocking its light creates a deeper, more noticeable dip in brightness.
That makes sense.
And because the star is cool, a planet has to orbit very close to stay in the habitable zone, meaning it transits frequently. TRAPPIST-1 has multiple rocky, Earth-sized planets packed into a space smaller than Mercury's orbit.
Which gives us plenty of chances to watch them pass in front of their star. And that sets the stage for the James Webb Space Telescope. We aren't just counting planets anymore, we are characterizing their atmospheres.
Right.
When starlight filters through an exoplanet's atmosphere, the different gases absorb specific wavelengths of light. It's like reading a barcode. We look at that filtered light and can say, oh, there's water vapor or carbon dioxide or methane there.
And the holy grail of that atmospheric characterization is finding candidate biosignatures. Specifically, we're looking for chemical disequilibrium. On Earth, oxygen and methane react and destroy each other very quickly. So if you see them both abundant in an atmosphere together, something like a global biological biosphere must be constantly pumping them back out, right?
I mean, that seems like a slam dunk.
Well, what's fascinating here is that even a strong signal like oxygen can be a false positive. Oxygen can easily arise without life.
Really?
For example, red dwarf stars emit intense ultraviolet flares. That radiation can split water molecules in a young planet's atmosphere. The light hydrogen escapes into space, leaving the heavy oxygen behind to build up. So you could be looking at an atmosphere packed with oxygen on a completely dead, irradiated world.
Oh, wow.
That's why we rely on that ladder of confidence. A single gas is never enough. We need contextual, repeatable evidence.
So hunting for microbes is an exercise in incredibly delicate chemical analysis. But if we are searching for intelligent civilizations, we need a totally different toolkit. We stop looking for biology and start looking for technology. Let's talk about SETI, the search for extraterrestrial intelligence. For decades, this has mostly been radio SETI. We point massive dishes at the sky, hoping to catch drifting tones or structured pulses that stand out against the random cosmic static.
And the greatest challenge in radio SETI isn't just listening to the stars, it's filtering out our own terrestrial interference.
Right, because we are loud.
Our planet is incredibly noisy. Satellites, aircraft radar, cell phones, even a microwave door opening in the observatory break room can mimic an anomaly.
Seriously, a microwave?
Yes, it's happened. Today, modern computation allows us to search massive data sets much faster, expanding our hunt into optical SETI, looking for brief, powerful nanosecond laser pulses and wider technosignatures.
Like what?
We're talking about searching for artificial atmospheric pollutants, massive waste heat signatures from planetary scale engineering projects, or highly anomalous transit shapes that don't look like round planets.
But here's the thing. Every time astronomers spot one of those anomalies, the public goes absolutely wild. A weird radio burst gets detected, or a
Yeah.
cabbie's star dims in an unusual asymmetrical way, and immediately the headlines scream about alien megastructures or distress
We
beacons.
have to be brutally rigorous about this. Unexplained signals are not automatically extraterrestrial technology.
Right.
The universe is incredibly complex, and most anomalies turn out to be new, natural astrophysical phenomena we simply hadn't seen before, or instrumental errors. The scientific discipline of SETI lies just as much in meticulously disproving false alarms as it does in hoping to find a genuine signal.
It feels like looking for a needle in a haystack and we don't even know if the needle exists.
Yeah.
To frame our ignorance on this, we use the Drake equation. It's famous for breaking down the odds of detecting a civilization by multiplying a bunch of factors. The rate of star formation, the fraction of stars with planets, the environment suitable for life, the fraction where life actually emerges, the fraction that develop intelligence, technology, and finally, the lifetime of that civilization.
It is a brilliant concept, but it is essential to clarify that the Drake equation is a framework to organize our ignorance rather than a solved prediction.
Okay, a framework.
Think of it like a massive funnel. Thanks to modern exoplanet surveys, the top of the funnel is well lit. We have excellent data for the astronomical terms. But as you move down the funnel into the biological and sociological terms, the odds of non-living chemistry becoming life, the evolutionary path to intelligence, or how long a technological civilization survives, we are completely in the dark.
Just guessing at that point.
Yes. Those numbers remain purely speculative.
And that deep speculation brings us face to face with the Fermi question. The Great Silence. If the galaxy is ancient, and there are billions of potentially habitable planets, and the universe has had billions of years a head start on us, where is everyone?
The potential answers to the Fermi question range widely, and many are quite sobering. It could be that the evolutionary leap to intelligence is incredibly rare, just a statistical fluke.
Yeah.
It could be that the physics of interstellar travel are simply too difficult, locking everyone in their own solar systems. Or, more ominously, there might be a great filter.
The Great Filter.
Right. Technological civilizations might have very short lifetimes. They might acquire the power of planetary transformation like nuclear weapons, engineered pathogens, or climate-altering industrial technology before they develop the social wisdom to survive those powers. Or perhaps they are out there, but they deliberately choose silence, or our search methods are just too primitive to hear them.
That idea of a civilization's lifetime, the Great Filter, really forces us to look in the mirror, because humanity is just starting to venture out into the cosmos. And as we do, we have to consider the massive physical realities of interstellar travel. It's not like jumping to warp speed in a sci-fi movie.
Not at all.
Even if we figure out how to travel at a fraction of the speed of light, you are dealing with immense energy requirements, catastrophic kinetic impacts. Where a single grain of interstellar dust hitting a hull hits with the force of a bomb-deadly cosmic radiation, and trips that take centuries.
And before we even tackle other star systems, we face profound planetary ethics right here in our own backyard regarding terraforming. Modifying the climate and atmosphere of another planet, like Mars, to suit human settlement is an immense multi-generational engineering challenge. But ethically, we have to pause and ask, if Mars has a hidden, indigenous microbial ecosystem deep underground, do we have the right to alter its climate?
Oh, that's a tough one.
Could we accidentally destroy that life or overwrite an irreplaceable scientific record just to make a backup Earth for ourselves?
Which is exactly why planetary protection protocols are incredibly strict at space agencies right now. It's not just a suggestion. We have to prevent forward contamination infecting other worlds with hardy Earth microbes hitchhiking on our rovers, and backward contamination, bringing something hazardous back here to Earth.
Right.
If we find life on Mars, we have to be absolutely sure it's actually an alien biology and not just a resilient Earth spore we brought with us.
The integrity of the entire search for life depends entirely on rigorous contamination control.
Now, speaking of visitors and contamination, whenever we talk about aliens, a huge portion of the public immediately points to UFOs, or UAPs, unidentified anomalous phenomena as they are called now. They see blurry infrared videos from Navy fighter pilots and say, look, they're already here, they're flying in our atmosphere.
This is where we must apply Sagan's rigorous skepticism. Unidentified observations do not establish alien visitation.
Right.
An ambiguous image on a camera sensor, a radar glitch, or an unexplained atmospheric phenomenon lacks the physical chain of custody, the reproducible evidence, and the independent verification required by the scientific method. If we are going to claim that beings from another star system have traversed the interstellar void to fly in our atmosphere, we need physical proof. Extraordinary claims require extraordinary evidence.
So what does this all mean? If they aren't here buzzing our oceans, but we are out there sending messages like the Pioneer plaques and the Voyager golden records, carrying our math, our music, our anatomical drawings into the void, what actually happens if we make contact?
Well, the challenge of cross-cultural communication would be profound. We often assume mathematics might be a universal language. But an alien civilization's sensory systems, their evolutionary goals, and their social organizations could be so radically different from ours that meaning is completely lost.
We might not even recognize it as language.
Exactly. Even if we detect a structured carrier signal, it might contain no decodable message for a human mind. Furthermore, we often use civilizational classification scales, like the Kardashev scale, which categorizes hypothetical societies by how much energy they can harness from a planet, a star, or a galaxy.
Right, like building a Dyson sphere around a sun.
Yes, but those are just human search heuristics. They are prophecies of inevitable development. An advanced civilization might not build massive, energy-hungry Dyson spheres. They might prioritize extreme efficiency, miniaturization, and low visibility.
It really highlights how the interpretation of a discovery would totally depend on the context. Finding a fossilized, single-celled microbe frozen in the Martian subsurface would be incredible for science, but it's a very different cultural shock than suddenly picking up a high-definition, unmistakable mathematical broadcast from a star system 50 light-years away.
Yeah, totally different scales of impact.
That kind of contact would completely reshape human identity, our religious and political institutions, and our understanding of our place in the universe over generations.
Pulling all these threads together, what the vast body of astronomical evidence undeniably shows is that the universe shares a common physical and chemical language. The carbon, nitrogen, and oxygen atoms in our bodies were forged in the hearts of dying stars. The laws of gravity, thermodynamics, and light are the same everywhere we look. That is our confirmed, tangible cosmic connection.
But the biological connection, whether the universe is teeming with life or silent, is still an open case.
Yes. And uncertainty shouldn't be filled with comfortable assumptions. The staggering abundance of exoplanets does not prove that life is common, and our current lack of confirmation does not prove that we are alone. We can only answer our central question based on the evidence we firmly hold today. We are physically and chemically connected to the cosmos, but the biological and cultural extent of that connection remains science's greatest open investigation.
This has been an independent COSMORA HQ book overview in audio podcast format. It is not an audiobook, narration, adaptation, abridgment, reconstruction, authorized production, or substitute for the original work. We've been discussing The Cosmic Connection, an Extraterrestrial Perspective by Carl Sagan. We strongly encourage you to legally access the original book to fully experience Sagan's arguments and vision. We also invite listener questions on this topic, and we'll leave you with this. Which discovery would transform humanity more profoundly? Finding simple life nearby, or receiving evidence of an intelligent civilization among the stars?